The elevator pitch for safeboot is that it makes booting Linux somewhat safer by replacing the built-in OEM and Microsoft UEFI keys with an owner-controlled key stored in a hardware token like a YubiKey, which is used for signing the kernel, the initrd, and the command line, as well as enabling all of the UEFI firmware features to ensure that the system will only boot the signed unified image and run it directly as a UEFI executable without an on-disk bootloader. Additionally, safeboot attests to the user that the firmware configuration has not been modified using a time-based one-time password, which tells the user that it's safe to enter their PIN to unseal the disk encryption key from the TPM. It also has scripts to enable Linux lockdown mode, as well as file system integrity protections, all of which together help prevent a range of hardware, firmware, and software attacks. There's a lot wrapped up in that pitch, and to better understand the resiliency of the safeboot configuration, let's look at how it prevents many classes of attacks, how it detects other sorts of attacks, and how it helps the computer owner recover to a safe state. Specifically, let's focus on an area that's often considered game over for most threat models, an attacker with physical access to the system, including internal access. This is out of scope for most threat models, although if we assume a reasonable time and dollar budget, so no decapping chips for instance, I think there's a reasonable chance of protecting our computers. To help look at it from an attacker's perspective, I've invited my hacker alter ego to demonstrate some common techniques for getting into Linux machines, as well as their research into physical security. So I'm going to give them access to my safeboot laptop, and I'm going to try to gain access or persistence on the device. First thing I'm going to do is put in a USB stick with a live Linux install and boot to the UEFI boot application menu to see if I can boot from that and start making some modifications. And that won't work, since the UEFI firmware will only boot a kernel that has a valid owner signature on it. The live Linux install probably has an official UEFI secure boot signature, but safeboot has removed the Microsoft key from the database, so it won't boot that image. So what's next? All right, no problem. Next up, I'll switch to the grub console and change the kernel command line to boot with rd init equals bin sh or something, so that I can modify the /boot partition, grub cfg, initrd, or the kernel. And there's no grub. It's going straight to the kernel. It has the signed image booted directly from the UEFI boot manager, so there's no grub.cfg to modify. Additionally, there's no grub boot hole to worry about. All right, no worries. I will go back to the boot manager and drop to the UEFI shell, and then boot a different kernel. You could try that, but the kernel command line is part of the signed image, so you can't override it via the shell. All right, then, we're going to do this the hard way. We're going to flip it over, and we're going to go inside. Two easy avenues of attack. First, there's the SSD, and then there's also the spy flash here. That might work on most systems, but when you try to boot it up again, you'll notice that you now need the firmware password to restart the machine. This ThinkPad model has tamper switches on the case and the disk, so you need an embedded controller exploit to reset the state of the switch if you've opened up the laptop and removed the disk. And I already knew about these tamper switches since I worked with Lenovo to fix that particular vulnerability. Luckily, let's pretend I have a embedded controller exploit, since like Alex Matrosov pointed out, it's not really a secure chip and not a secure boundary. So I can mount this disk in another machine and then replace the kernel and the initrd with one of my own. And that would work if the system were using grub, since trusted grub doesn't include the initrd in the signature. But safeboot A doesn't use grub, and B includes the kernel, command line, and initrd in the signed executable. You can't replace any piece of it without access to the signing key, which again is stored in an offline hardware token. All right, we're going to have to do this the hard way. Pull out my flash programmer, and I'm going to clip it to the flash chip here to modify the secure boot variable in the NVRAM to turn off signature checking. So now my modified kernel and initrd will boot, and it can ask for the user's PIN on the next time they get access to the machine. While that will give you a kernel running on the machine, the TPM won't display a valid TOTP token, since the UEFI secure boot related variables are also included in the sealing authorization. The user will know that they're not talking to a valid kernel. While I'm in there, I leave the secure boot on, but I change the platform key to one of my own, and then I assign my own backdoored kernel and copy that onto the disk. Same thing. The keys are included in the sealing state. So modifying it prevents the TPM from HMACing the top P secret, as well as unsealing the disk encryption key. Okay, next up, maybe there's a older signed version of the kernel with a security vulnerability. So I can copy that one to the disk and roll back to that one instead. So now the machine will boot with the UEFI platform key controlled by the owner, and I now have a running kernel to try to trick the user. Just because the signature is valid doesn't mean that it's acceptable. The TPM has a monotonic counter, and it won't match the signed one for that older kernel. So the TPM won't HMAC the top P secret. Again, the initrd won't display a valid top P, so the user will know that there's been a rollback. But the PCRs used to authenticate to the TPM are not actually secret. So while I have the device open, I can pull out my LPC tool to pretend to send the right values to the TPM and then just ask it for the disk encryption secret. The user pins only a few digits, so a few thousand tries, and I'll have it. The sealed disk encryption secret is protected with the TPM's dictionary attack counter, so you're both going to be rate limited by the TPM hardware, and you'll get locked out after a few tries. You need to get the pin from the user somehow. Okay, so the fake kernel needs to be able to produce the top P code, so we need to find the top P secret. Again, using the LPC tool, we can send the PCRs to the TPM and just ask it for the secret. Well, that would work for the TPM v1.2 top P, but TPM2 top P is a significant improvement, since the TPM2 will do the HMAC internally without ever revealing the secret to the OS. All right, well, while we're talking to the TPM, we could pre-generate a set of those one-time passwords for a range of times into the future. That could work, although it limits your time window to get the system back to the user, because you have to have generated a response for that time, and you have to get them to type in their PIN during that window. This is also an area of research. We need to look at if the HMAC can be rate limited, which would make it much harder for you to compile that dictionary of future values. I guess that means it is time to put this under the microscope and pull out the nitric acid then. Yep, that's totally doable, and it's expensive and invasive. There's not much we can do about it on a commodity system to protect against that sort of attack. Likewise, if you have a 0-day against boot guard, and you could add some sort of firmware bootkit to the spy flash. All right, well, let's shift gears then, and let's assume compromise. Let's say I've got code execution on the OS, I've escalated to root, so my next goal is to gain persistence. From the previous attack attempts, I know that changing the kernel or the initrd in /boot won't work due to the UEFI secure boot keys. And it looks like the root FS is mounted read-only, so mount-o rw remount / and I'm going to put a bootkit in there. So you're right, the block device is read-only, since it's going through the dmverity module. Safeboot borrows this idea from Android, Chrome OS, and Core OS to make the runtime system immutable, and to protect it with the cryptographic Merkle tree. The root hash of this tree is included in the signed kernel command line, so any modifications to the root file system are going to be detected, and changing it requires the offline sign-in key and a hardware token. All right, well, let's try then exfiltrating the sensitive corporate data onto this USB flash drive. Plug that in, and it's not mounting. Well, Safeboot has added the USB module to the deny list, so it's not going to mount. But that list only prevents modprobe from loading modules, so I can still do an insmod USB storage.ko. It's not signed by a trusted key, so that you can't load that module. Okay, I'm going to dd if dev mem, see if I can find the encryption key and use that to decrypt the copy of the disk I made when I had it out of the hardware. Well, thanks to the tireless effort of Matthew Garrett, the lockdown patches prevent that from working. The lockdown equals security mode is the default if UEFI secure boot is enabled, and safeboot enables the stricter lockdown equals confidentiality mode. Okay, we're going to kexec into a new kernel that doesn't have those restrictions. Lockdown also checks signatures on the new kernel via the kexec system call, and the TPM won't unseal the keys since the PCR will attest to the entire boot chain, including the current running kernel and then your attempt to boot into the modified one. All right, well, let's continue to assume compromise. Make it a little more interesting. Maybe I'm a malicious insider, and I want to connect to the corporate resources inside the firewall and exfiltrate them to my compromised machine. So I'm booting into my own kernel and initRD, and I try to SSH in with the user certificate. Luckily, the TPM measurements are a bit harder to fake. In order to authenticate, you need a quote from the TPM2 attest program with the PCR values that include the loaded kernel, the initRD, and the command line. And since the kernel command line also includes the tmverity root hash, it implicitly also includes the entire runtime of the system. The remote attestation server won't return a one-time authorization without those values. Okay, so I'm going to reboot this machine into a clean configuration, generate an attestation from that configuration, send that to the server, and then I'm going to reboot into the modified config before the reply comes back. The attestation key used to seal the authentication data is generated with the stclear attribute, so it's only valid for this one boot. Rebooting invalidates the ephemeral key, so it can't be used to access the authorization value. But I have another machine without boot guard, so I can fake the TPM PCRs. And this quote then will have the correct PCR values for the clean firmware, kernel, and so on. The TPM endorsement key is unique per device, so the remote attestation server won't even look at the quote since it came from an unknown machine's TPM. All right, I'm going to bring this back to the bench, and I'm going to desolder the TPM from the valid machine and then move it to the unprotected one. Yeah, that'll work. One possibility is to use the FTPM in the management engine instead of the discrete TPM, since the BGA PCH, Platform Controller Hub, is much harder to replace than the SOIC TPM. If the modified hardware is detected, the individual TPM authorization to the remote resources can be revoked, so at least this can be shut down. It's not a total class break. Although trusting the ME, in this case, has its own separate set of threats that you have to be worried about. That's true. And since the ME tells the x86 about the boot guard configuration, it's inside the TCV no matter what. Do you want to talk a little bit more about your recent research there? Sure. The sleep attack, CVE 2020-8705, was disclosed a couple weeks ago in November, and it allows a local attacker to gain code execution in ring 0 when the system is resuming from sleep. The root cause is essentially a time of check, time of use vulnerability in the boot guard ACM, where it checks the OEM signature on the firmware when doing a cold boot, but skips it when resuming to make the wake-up process faster. It loads code from the flash, however, so somebody with something like a SpySpy, one of my open source flash emulators, can provide a modified version of the firmware that will be trusted by the system. SMN is also unlocked at this point as well, so they can escalate to ring -2. I'm really glad that Intel considers this sort of physical threat in the boot guard attack model, and that they've addressed it in the fix for the CVE. For too long, local physical attacks were out of scope for most of these threat models, and it's a really important step that they're taking them much more seriously now. Thanks so much to my alter ego for their help in this walkthrough of some of the threats that safeboot is considering. For more information about safeboot, you can check out safeboot.dev. However, it's really important to note that what's included in this is not custom firmware or radically new architectures. Safeboot is about enabling the existing security mechanisms in the commodity UEFI firmware and in the mainline Linux kernel. And that's one of the reasons I say that safeboot is just an incremental improvement on boot security. CPU issues, OEM firmware bugs, and Linux vulnerabilities are still very much concerns. However, if we can reduce the attack surface, we can harden the configuration, and we can have ways to detect many types of attacks, then we can really raise the difficulty of launching an attack and force the attackers to use much more sophisticated methods. If they have to burn 0 days to get after the machine, that's a much better situation. And these UEFI secure boot features used by safeboot are present in almost every modern system, though they're not enabled by default. And in fact, many Linux and even Cube's install guides start with turn off secure boot, which is really unacceptable for modern platforms, since it means that there's zero integrity protection for the bootloader, for the kernel, the initRD, the file system, and so on. Even if you leave secure boot enabled, the default configuration doesn't secure as much of the runtime as you might expect. Only the grub bootloader and the kernel are signed. The kernel command line and the initRD are unprotected. I'm disappointed that the Linux community hasn't adopted a secure by default approach that companies like Apple and Chromebooks have done. iPhones no longer ask you if you want to enable disk encryption, but it's an advanced option on an Ubuntu install. iPhones no longer ask if you want to store encryption keys in a hardware enclave, but try to find a concise guide to doing so with the TPM in Debian. Chromebooks don't ask if you want an immutable file system with integrity protection, but again, try to find an easy way to enable DM Verity on Fedora. Chromebooks don't ask if you want to remotely attest the firmware configuration before authorizing access to your Google account. Are there any other services that are doing this? As a community, we need to do so much more to make usable security usable. As Swift on Security pointed out, if we don't make it usable and secure, the users will make it usable and insecure. So my take-home message from this talk is not that you should install safeboot on your machines, though please do so we can improve it and we can make it more usable. Instead, my take-home message is that safeboot should be just part of the default configuration and you shouldn't have to install it. That we really need to work with the distributions to ensure that everyone's machine is configured in a secure way by default. Until then, however, we need to do what we can to protect our devices, and hopefully safeboot is part of that. So again, thanks for listening to the talk, and I'd love to answer any questions that you all might have.